Hi everyone, today I would like to show you how can we use machine learning to make concurrency testing more efficient. This work is a collaboration between Purdue University and Google DeepMind. Concurrency is heavily used in the kernel, so it is important to make sure the kernel behaves correctly under concurrency. Otherwise, we would have concurrency bugs, a type of bugs that depend on the instruction schedules of threads. Concurrency bugs often have serious impact on the system. For example, earlier this year, a new vulnerability called stack rot was discovered in the Linux kernel. This vulnerability enables privilege escalation, and its root cause is a concurrency bug. Apparently, we want to avoid problems like this, which means we have to find the kernel concurrency bugs. But how can we do this? Concurrency testing is one commonly used approach. The typical pipeline of concurrency testing has two major steps. In the first step, test generation, we need to find a pair of test inputs for different threads, because concurrency testing requires running code in different threads. Each input is a user space program and invokes the kernel APIs, which are system calls, so that some kernel code will be triggered to run. Next, because concurrency bugs only expose under some specific schedules, we have to propose a schedule, so that the kernel threads will run in an order that is likely to cause bugs. After a test is generated, we then can execute it on the kernel to find the concurrency bugs. To improve this pipeline, prior work mostly focuses on improving test generation. There is a lot of work in this area, including our own. These systems try to find promising tests by construction. They use heuristics, they use static analysis to find the pairs of inputs that are effective at testing concurrency, so that we don't have to enumerate every pair of inputs. While these systems improve the testing effectiveness, there is another challenge that has to be addressed. That is the efficiency challenge. One problem we found by analyzing a lot of executions of tests is that many executions are not interesting. They are redundant. For instance, the test did not exercise any new code during the execution. This is a big problem because the concurrent executions are not cheap. In our setup, it takes almost 3 seconds to execute one test. Because we have to set up VMs, we have to instrument the execution to control kernel schedules and detect bugs. A typical concurrency testing workload can have millions of tests. If we have 1 million of tests that are redundant, we'll waste 1 month of machine time. And this is why it needs to be addressed. One way to address this problem is to run tests more selectively. It means we only execute a subset of the generated tests, but make sure the tests in this subset are more interesting. So we ask ourselves this question: can we identify interesting tests and then we only execute them? If we can add a test filtering step here, in which we filter out all the redundant tests, then we could achieve great testing efficiency, since now only the interesting tests will be executed. Another advantage of this test filter is that it will be a composable mechanism. It means it can be piped after any existing generation techniques we have seen before to make them even better. To implement this new pipeline, we first have to figure out what are interesting tests. How do we define interesting? Well, we can use coverage metrics such as code coverage. Let's say we have 2 threads that execute this code. The thread on the left side will first update a shared variable x. It will run some other code after that, but in the end, it will check the value of variable x and then decide whether it will call a function or not. The thread on the right side changes the variable x. When we do the concurrency testing of these 2 threads, we should propose different schedules to test, and the code coverage can tell us if the schedule is interesting. If we run the thread on the right side first, and then we run the left thread, this won't be an interesting test because we do not cover any new code under concurrency. In contrast, if we run the right thread after the left thread updates the variable x, but before it checks the value of x in the end, this is an interesting test because now we can trigger the function handle issue to run. In other words, an interesting test should exercise new code that others cannot. So how can we get the coverage of the test? We can collect the coverage by executing it, but wait a second, we just said it is expensive. We want to avoid executions but still get the coverage. How? It looks like we have to predict. If we can predict the coverage, then we can identify the interesting tests. In Snowcat, we chose to implement this predictor using machine learning. This decision is motivated by success achieved by machine learning in predicting the application coverage. However, when it comes to the kernel and concurrent executions, there are two major challenges that we have to address. The first problem is how can we represent a concurrency test as a query to the model? The inputs in the concurrency test are user-space programs, executing the kernel APIs. The schedule, on the other hand, describes the ordering of kernel threads that are running kernel code. We can see they have very different semantics, and this big semantic gap might make it very hard for the model to work well. The second problem is that predicting the kernel coverage is actually quite expensive. A Linux kernel could have over 2 million of code blocks, and predicting a graph that has a similar amount of blocks might take 3 seconds. This is already longer than dynamic executions that we want to skip. That means we need to make the prediction much faster, because otherwise the predictor will be useless. In the next, I will show you how do we address these two problems. Here we have the inputs and the schedule. They are far away from each other because of the big gap between their semantics. So how can we connect them? Our idea is that instead of using the inputs, we can represent the schedule based on two control flows. The control flows triggered by the inputs. This is how it works. Each input in the concurrency test will first go through a kernel sequential execution profiling. A sequential execution means the kernel thread runs alone without other threads, so there's no concurrency, there's no interference. We execute this input on the kernel, so the kernel will run some code to handle it, and we collect its execution trace. For example, the kernel might execute 3 lines of code highlighted in yellow. Here, the function call to handle issue won't be covered since the kernel thread runs sequentially without concurrency. Based on this execution trace, we can extract a kernel control flow triggered by the input A, which is shown in the middle of the screen. This control flow collection will happen for each input, which means we will also collect the kernel control flow triggered by input B. In the next, we'll focus on representing the schedule. What we will do is to extract the ordering requirements from the schedule we're planning to test. For instance, we hope to run this code before another code. Because these ordering requirements are relations, naturally they can be represented as edges based on these two control flows. Once these two control flows are connected using schedule edges, we can see that this graph can represent a concurrent execution we want to run. And this is what we will provide to the model and ask for the coverage prediction. Speaking of the coverage, as we discussed before, it will be perfect if the model can predict every code block in the kernel, but unfortunately, it is too expensive. To make the prediction faster, our idea is to make the task simpler. That means instead of predicting everything, we'll just predict a few blocks, but make sure they are the most important blocks to predict. This idea brings us to a new concept which we call adjacent uncovered blocks, the blue blocks in this graph. These blocks are adjacent to the already covered control flows. Remember, these control flows are covered sequentially without concurrency. Here's one example of this block. In this code snippet we have seen, the blue block, the function call to handle issue, cannot be covered sequentially without concurrency. So predicting the coverage of it will be important because it can help us find interesting tests that can trigger this new execution path. To let the model know we want to predict these blocks, we'll add them to the graph. As we can see, the blocks in this graph is only a subset of all kernel blocks, and this subset is much smaller than the complete set. On average, it is only 0.5% of the complete graph. This is how we can make the prediction faster, by predicting a small but important subset of the kernel code blocks. We provide this graph to the model and essentially ask this question. Here's the graph. It represents a concurrent execution we want to run. Please tell us the coverage of every code block in this graph. So the model will tell us if the adjacent uncovered blocks will be covered. In addition, it will tell us if the sequentially covered blocks will be skipped because of concurrency. This is also important to know since that implies a different execution path as well. This graph shows a general idea of how do we represent a test and ask for the coverage prediction. In our actual design, the graph can encode more information about the concurrent execution. For instance, we'll add edges to indicate the possible data flows that can happen between blocks, so the model will know more about the thread interaction. We leave these details to the paper. To implement the Snowcat, we need to train the model and integrate the model into a testing framework. Training a model requires a training dataset. In total, we collected 1.3 million examples, and what we are hoping is that after seeing these examples, the model will be able to generalize. Means it should work on new concurrency tests that have new inputs or new schedules. Finally, this dataset is collected on the Linux kernel 5.12. When it comes to the model design, our model has two major components. The first component can learn the semantic of each individual code block. Specifically, it is a BERT model that learns the assembly code of kernel code blocks. And the second component, the graph neural networks, can learn the connections between blocks. We train the graph model using graphs that represent the tests and their coverage. Next, to use this predictor for testing, we integrate the model into existing systems, including PCT, Riser, and Snowboard. We first train a model and test the Linux kernel 5.12. We compare the number of data races found by Snowcat and PCT. PCT is a state-of-the-art concurrency testing approach. The y-axis shows the number of unique data races detected after running the concurrency tests, and the x-axis shows the number of days spent on testing. First, we can see that when both testing the kernel for 12 days, Snowcat can find 350 more data races, which means it is more effective than PCT. Second, to reach a fixed amount of data races, PCT had to spend over 12 days, but Snowcat only took 6 days. It is about 2 times faster. After analyzing the data races, we found Snowcat is also more effective in terms of finding new bugs. We discovered 17 new concurrency bugs, 13 of them are confirmed, and 6 are fixed. These bugs came from different components of the kernel such as file system, network subsystem, and drivers. They have serious impact on the system such as causing data loss and denial of service, and some of them existed for years. But unlike other systems, to achieve this high efficiency and high effectiveness, Snowcat needs to collect some training data and train a model. For instance, the model we used takes about 10 days to get. There's a little concern here. For instance, when it comes to a new kernel, do we have to spend another 10 days training a new one so that we can find new concurrency bugs? It turns out, the training cost for a new kernel can be reduced or even skipped. First, if training a new model is expensive, how about we keep using the same one? By using the model that is already trained, we can skip the training step. We evaluate this idea by testing Linux kernel 5.13. This kernel was released 2 months after 5.12, with 17,000 of new commits. The graph here shows the result of Snowcat using the old model. We can see that Snowcat is still achieved higher efficiency than PCT. It is 1.5 days faster when they both tested the kernel for about 7 days. In fact, when we use the same model to test Linux kernel 6.1, which was released 1.5 years later, will achieve similar results. The model is still effective on a 1.5 years later kernel. These results are encouraging because it shows that the cost of the base model, the foundational model, might be a one-time cost, and we can amortize it as we test new kernels. This is also a big relief. Snowcat works fine even if we use the same model. But we did not stop here. We tried another way to reduce the training cost. That is to incrementally update the model by fine-tuning. What does fine-tuning mean is that instead of training a new model from scratch, we train a new one based on a model that is already trained. Very often, because the base model is already good enough, the new model can have great performance even with very little fine-tuning. We take the model trained for 5.12, fine-tune it with a very small amount of data collected on this new kernel, so the new model can get a rough idea of what's new. Because the new dataset is small, fine-tuning only takes 1 day. And what we found is that the fine-tuned model can significantly improve the testing efficiency. Now Snowcat is 3 days faster than PCT. This exploration shows that by incrementally updating the model, Snowcat can also achieve great testing efficiency. In the paper, we provide more details about Snowcat. If you are interested, please read the paper. To sum up, Snowcat uses machine learning to improve kernel concurrency testing. Specifically, it trains a machine learning model to predict the kernel coverage for concurrency tests. Our evaluation shows that the efficiency and effectiveness of testing can be improved with ML, and its artifact is released and evaluated. Thank you very much.
Okay, we have plenty of time for questions. Yes, please.
Hi, my name is Levy. From affiliation is UC Berkeley. I just have a couple of questions for the author in regards to the machine learning model. In that some similar approach was used before in analog circuit design in terms of the Bagnets paper published in ICAT in 2019, which used a neural network, a DNN, as a filter for expensive simulation in circuit or in analog circuit design. I was wondering if there is some sort of similarity, and if you could comment on whether or not these approaches are similar in terms of generating test coverage. And more importantly, there was one paper that came afterwards in 2020 by Professor Bora, which mentioned about the using learning-based methods, whether that could work a little bit better and generalize a lot better in terms of predicting test coverage.
Do we actually have the author online? Yeah. And he heard the question. Yeah, okay, he's up. Marginally, it's very faint. Say something. Yeah, no, it's better.
Hi.
Yes, go ahead.
I got the question. So you're asking whether the similarity between the Snowcat approach and other papers published in other conferences, right?
Uh-huh.
Okay. So I think as you mentioned in the kind of middle of the slide, there are some existing approaches that try to predict the coverage of applications or hardware design. I think to highlight my issue is common. We want to predict something about execution of the application of the hardware. For instance, the coverage, we want to predict the coverage. But the biggest difference is in the Snowcat, we want to predict the kernel coverage and to use a great capacity. For instance, one paper we actually discussed one work that we discussed in the paper is someone from Google that tried to predict the hardware coverage. And the two numbers I can give you show the difference. The hardware they want to predict only have thousands of unique blocks, and we have millions of blocks. So this is kind of the capacity that we have to deal with, and this is why we have to come up with results such as adjacent uncovered blocks to address this problem, to make the prediction faster, to make the prediction scale to real-world scenarios.
I see. Would a learning-based model work not scale just as well?
We haven't tried that, so I couldn't give you an answer. But I'm sure there are a lot of ways to optimize the prediction speed. But what we want to do is to make the prediction and just faster, out of the past faster. So this is why we want to solve the problem design itself, to focus on a few blocks of the kernel, rather than go through each other blocks to see if we can improve the speed by 5 times or 10 times.
Awesome. Thank you so much. That was a great talk.
Jeff Kenning, Harvey Mudd College. Code coverage is great, but there are a lot of concurrency bugs that involve going through the same code. A simple example is failure to lock something. I saw in your slide that you mentioned annotating the graph with some data flow stuff that you didn't mention in the talk, and I'm wondering, do you handle situations like failure to lock? And if not, is that just future work?
Yes, I love the question. So, I guess to answer your question, a short answer is we can use more metrics rather than code coverage. In the field, we have to have really different metrics that can tell you whether the path is interesting or not based on the coverage, based on whether it will cover some new code. For instance, another metric we have is to see whether the execution shows a different feedback. In this branch is different. That branch is not different. I think that will cover the case you mentioned. The loss is not released, right? Because the branch will not be different at that time. So it's different.
No, I'm not talking about lock not being released. I'm talking about simply not locking. There is a bug where there is no lock, and so in many situations you will flow through that code, and if there's no concurrency, everything will work fine. But a different execution path, you will have a race condition with the data, and you're going through exactly the same code, but you get different results depending upon sequential ordering.
I see. I think that if the data is passed between the two threads, cause one thread to execute a different path, right? For instance, one thread updates the variable, and then another thread writes the variable, and then we different execution path. That will be called by Snowcat using the predicted coverage. But if the data is very simple, it means no control exchange, we can catch that case, I would say.
Can I ask the people asking questions to please be concise and to the point? Thank you.
Hi, Brad Karp from UCL. Thank you for the talk. I thought I saw a pattern in the results, and I wanted to ask if you have an interpretation of the pattern. Namely, as the days went on and you were finding more and more bugs, it seemed like PCT and Snowcat found a very similar number of bugs toward the beginning and were sort of neck and neck for the initial number of days. But then later, after more days, was when the separation seemed to occur. I was wondering, is there an intuition for why that happens? Why doesn't it steadily do better from the very beginning?
I think one possible reason is that usually when we do testing, increase the coverage at the beginning is relatively easy. But climbing the coverage in the end is kind of become hard because that requires very precise approaches to enter different states of the kernel, right? And this is why I think Snowcat becomes better at the later stage, but at the beginning, they're kind of very similar.
Thank you.
Does that make sense?
Yep, thank you.
Okay, last question.
Hi, Matthias Hille, Barkhausen Institute. I was wondering how your approach applies to smaller code bases, like microkernels, for example, where I might not be able to generate 1 million tests. Is that enough to train a model like yours?
I think so. Nothing is preventing you to try that. But I think if the application, if the software you want to predict is kind of small, it's much smaller than the kernel, you may want to try other methods, including Snowcat. Yeah, try different stuff, I think.
Okay, thanks.
Okay, let's thank the author again.
Thank you.